All right, in the first video in this series, we tried finding the slope of the tangent line to a curve at a point by using the limit process. Then we used the same definition to define the derivative of a function. So now we're going to try to understand the relationship between differentiability and continuity. And I'm going to give you some heads up here that I'm going to get this result at the end of this video. And what is this result? If f is differentiable at x equals c, then f must be continuous at the same point. So you can take this as like this. If f is not continuous at x equals c, then f is not differentiable. Okay, so sometimes you prove that the function is not differentiable by just showing that f is not even continuous. So that would be enough. But if f is differentiable, and if you know that, then f must be continuous at point c. To prove this result, we're going to use an alternate definition of derivative of f at a point. In fact, in the past, we started with the point c and f of c, and the run here was delta x. But right now, we're just going to choose another point on the curve, another arbitrary point on the curve, call it like x and f of x. And this way, run is going to be x minus c. But the goal was earlier to let a run go to 0. And if we do the same kind of like approach here, so x minus c is supposed to approach 0, which essentially means that x must approach c. Okay, so now the rise over run is going to turn out to be f of x minus f of c divided by x minus c, which is the run, and we were letting x approaching c, and this limit is just equivalent to the earlier definition of the derivative at point c. And recalling from chapter 2, when we talk about the existence of limits, we also talk about the existence of one-sided limits, and this is the same limit as x approaches c from the left, and same limit again as x approaches c from the right. And for the limit to exist here, which is the alternate form of the derivative, one-sided limits must exist and must be equal. And we have a special name for one-sided limits that I just described in the previous slide. These are called derivatives from the left and from the right at point C. So this follows that f is differentiable on the closed interval AB whenever it is differentiable on the open interval A and B, and the sided limits at the end points both exist. Okay, when a function is not continuous at C, it's also not differentiable at C. That again, it follows from this result that the negative of this expression in an if statement implies the negative of this statement. So a negative of the statement number 1 is implying the negative of statement number 2. If f is not continuous at C, then f cannot be differentiable at x equals C. And here's an example that we worked on in chapter 2. This function is called the greatest integer function. It's like a floor looking like function. And this function is not continuous at the integer values, and specifically at x equals 0. So if you use the limit definition of the derivative of this function at 0, you will see that this limit does not exist. And again, you can check the limit at other integer values, and you will see that f, this greatest integer function, is not differentiable at the integer values. To solidify this concept, why don't we look at the left and right limits at specifically x equals 0. All right, let's check that out. So let's approach 0 from the left, and we're looking at f of x minus f of 0 divided by x minus 0. On the left of 0, going back to this graph here, on the left of 0, so we are somewhere here, right? So the function takes the value of -1. Okay, so essentially, which means that this greatest integer function takes the value of -1 for sure. And f of 0 is already 0, and you're dividing that by x. So look at this limit here. So this limit turns out to be the limit of -1 over x as x approaches 0 from the left. So x's are very close to 0 but negative. So -1 divided by something very small but negative is going to take you all the way to plus infinity. So that's why this limit is plus infinity. Let's look at the right limit here. So we're approaching 0 from the right. So we're looking at the same kind of like rise over run, f of x minus f of 0 divided by x minus 0. But since we are on the right of 0, I'm sorry, since we are on the right of 0, we are talking about x's somewhere here, right? But approaching 0. So the function's value on the right of 0 is just 0. So for that reason, this guy takes the value of 0, and this limit turns out to be the limit of 0 minus 0 divided by x, and x approaches 0 from the right. But here, this 0 is an absolute 0, right? 0 minus 0 is not in the limiting sense, but this x approaching 0 is in the limiting sense. But we know that 0 divided by any number, doesn't matter how close x to 0, 0 divided by that number is going to be an absolute 0. Okay, for that reason, so this limit here is going to be 0, and as you see that the left limit is not the same as the right limit. So for that reason, f is not differentiable. And we know it from chapter 2 that this function is not even continuous because there's breaks in the graph of the function at the integer values. So we in fact concluded that f was not continuous at x equals 0. Now we're just showing that f is not even differentiable at that point. And that again follows from this result here saying like if f is not continuous then f is not differentiable. In fact, we could immediately conclude this by using the result that we proved in chapter 2 that the greatest integer function is not continuous at the integer values. So presumably it's not differentiable at the integer values, specifically at x equals 0. Here's another example that we went through. So the function is absolute value of x minus 2. Well, this function is continuous though at x equals 2. This is something that follows from chapter 2 because again there's no break on the graph. There's a cusp here or corner here, but still you can graph the function without taking your hands off, right? But now we're going to prove that f is not differentiable. So continuity is not a guarantee for differentiability. In fact, you can construct lots of continuous functions, but not differentiable. Okay, so here we go. Let's try to use the limit definition to show that this function is differentiable at x equals 2. I'm going to look at two limits. One is me approaching 2 from the right, and the other one is me approaching 2 from the right, from left, from right, okay? So let's check what's going on here. So we're looking at f of x minus f of 2 divided by x minus 2. And on the left of 2, well, the function is absolute value of x minus 2, but on the left of 2, inside of the absolute value is always negative, right? Because if you plug in something less than -2, that number minus 2 is going to be negative. So the absolute value function is going to take the value of minus x plus 2. It's in fact a negative of inside. Okay, so for that reason, this whole fraction is going to turn out to be a negative x plus 2 divided by x minus 2. In fact, you can also say that this is equal to negative of x minus 2, x minus 2. So this tells you that once you use the dividing out technique specifically, so you can prove that this limit is going to be -1. Okay. Let's look at the limit as x approaches 2 from the right. So the function is still the absolute value function, but let's see what it is equal to. So for numbers bigger than 2 but close to 2 is going to make this difference positive. So for that reason, absolute value of x minus 2 is going to be just x minus 2. So this ratio here is going to be x minus 2 over x minus 2 by the dividing out technique. So this is going to be always 1 no matter what x is. So then that limit is going to be just 1. All right. So this shows that the left limit, in other words, the left derivative is -1 at point 2, and the right limit is 1, which is the right derivative. So right derivative is not equal to the left derivative, so that makes f not differentiable at x equals 2. This simply implies that there is no tangent line to the curve at x equals 2 because in fact there are multiple lines that you can graph. They're all tangent, so that implies the non-existence of tangent line at point 2 because if tangent line exists then it must be unique, but in this case I can draw infinitely many lines passing through that point and each of which could be a tangent line, but that implies that a uniqueness is failing here, so we conclude that there is no tangent line at point x equals 2. All right, there comes the result that I have shown you in the beginning, right? So that if f is differentiable, then it's automatically continuous, and if f is not continuous, it's automatically not differentiable. Okay, and especially when the graph of a function has like sharp turns or a vertical tangent line, that's when we conclude that f is not differentiable. All right, we're done with the last learning objective of this section. So thanks for watching. I'll see you in another video. Bye.